Okay, now I'm going to share my screen. If I am not to be visible, so please let me know. Okay, done. So hello everyone. Welcome to all of you again in this session. Today will be the last day of our webinar. I hope you all enjoy this session. And regarding this session, you learned many things. I hope our main agenda was that you are all to be familiar with our software, which is a NanoDcal and rescue software for simulation and for making the devices and materials at nano level with working with atoms and molecules. This was the device studio. So uh, I think it will be help to all to make your research experience easy to good with our software. And basically our software are very user friendly, that can you see here. So in taking with the next step, I will be demonstrate some doping type devices today, and also I will create a structure device and try to demonstrate to all of you how to find their photocurrent structure as well, photocurrent parameters as well. And after if anyone wanted to familiar with MATLAB, if she or he calculate the DFT calculation on MATLAB, I will be all the steps I will be. So we kindly request to all of you. We provided you a software license up to 2 months. They try via their self and try to familiar with the software. And if anyone is facing any type of issue, they can directly ask us. We are here for you. Okay. So uh, okay, we are ready to. I will going to open my device studio and tell the things about some another step. So first, as all know, where our device studio is. Okay, I'll do it. I will do it some diode. So first, you have to go on your device studio, which is saved in C drive and in bin folder. As you can see, your file directory is open. Now this is device studio. Let's open it. Just give me a second. So know all this. If someone wanted to create a new project, he can or she can directly create a new project, or if they wanted to go into the existing project, simply browse it, and I'll save that project is here in the webinar section. I'll just check there. So the file, file directory is open. Now, so for doping type structure, wanted to make, there is a tool in the device studio called PCA. You can all say, as you can all say, when you go into the NanoDcal, there is a VCA that is stand for virtual crystal approximation. It helps to dope. It helps to doping the structure. Okay, so we using this VCA tool, we will try to create some structure. So okay, so I will be try to make a device which is made with some silicon 100 orientation, and I will then after I will try to dope with p-type and n-type doping with that device. Okay, so first we have to let first I wanted to show you some consultation part, how to you calculate in BC. So let us start it. So first we have to take silicon atom. So I will take the silicon one. So like I'm going to taking a silicon. Okay. Again, as you all know, uh, there is a file directory import in import local, and in 3D materials there is a semiconductor, and in semiconductor there is a silicon. So this is your silicon. Now we have to create a virtual crystal approximation for this silicon. So you have to go on simulator, then NanoDcal, and then BC. As you can all see, there is a two way to method. There is a two method to doping, which is a mixture vacancy and mixture atom type. As you can all see, our default atom, that is silicon, is automatic selected, and their basic set is also Sonia, which is LDA and PB. You can all see this is a doping type structure, N type and P type. P-type doping is already selected, and for value, uh, this value comes default 0.99 for P-type, and for N-type 1 point something values are coming default value. I'll let me all some another things I'll have to show. So like first I wanted to show how concentrations you calculate in the virtual crystal approximation. So you have simply do not do nothing. So I will choose here. When you click, I will try to do with P type. VC, I will calculate VCA calculation for P type. So simply you have to click generate file. So you can see here. I think. Let open this. Okay. I'll do it again. Have to do it again. Yes, since before this project, I simulating some project. Maybe this can. So I have to go on simulator, NanoDcal and BCA, and then here you can see default mixture vacancy is selected. Your element is selected, silicon, basic state, doping type P type, and click generate files. So generate files, not this one. See, is it working? So when you click generate files for VCA input, VCA calculation, simply there is a file that will be created, named with VCA.input file. And second one is silicon, whatever you choose your structure, like if you choose the gallium, or if you choose indium, like whatever type of semiconductor you choose, that file will be generated for them. VCA input will be default, and this value will be shown. This is the mat file in which their parameters will be shown. First, we have to calculate VCA dot input. You do for VCA dot input. This VCA dot input file is when you open it, you can see here. This here 0.99 is shown. That means p-type doping is selected. Okay, so you do have to first calculate it. So simply go on and click run option. You can see your job status window is shown here. Tab, and if you wanted to see the status of your calculation, you have to do this, and you can see the calculation is completed. I think if you wanted to see your calculations completed or not, you have to simply go on containing folder, and this folder you will be send it to you that where this file directory are saved, your project are saved. You can simply, there is a mat files is generated for your p-type doping. Okay, so now again, after the calculation of p-type, you have to uh, MATLAB is open. You have to close it. So after the p-type calculation, you have to select the n-type doping. So simply you can go in simulator, NanoDcal, do it VC again, and here I will select the n-type doping. You can see when I put the n-type, the value is changed automatically. This is the default value for silicon. So you have to simply click on generate file. So when you click generate file, there is another VCA.input file is generated here. So let it become generate opening. See, when you click here, there is another VCA.input file for 0.001 is generated. If you wanted to see which file is selected, now open with, you can see 1.00, this value is changed. That means it is an n-type doping. Okay, now you have to calculate it again, that is run it, and after running, we see the concentration, how concentration is having this structure. So you can see in MATLAB. So I will show it in MATLAB. So let the calculation is completed. See, your calculation is completed. So you have to go on open containing folder. There is another mat file is generated for this n-type doping. Okay. So first we have to calculate some things for this value. So go into the MATLAB and see here, it's already selected. Locate this file directory. You have to simply load these values and calculate some parameter. Since it device studio software default value is selected like 0.99 for p-type and 1.001 for n-type, the doping concentration is 1000. Okay, for p-type doping is zero to value will be the 0 to 1, greater than 0 and less than 1. For n-type doping, the value will be greater than 1. So which user can modify it according to your doping concentration. If someone want to change their doping concentration, they can do it. So now I'll have to calculate this. So simply you have to load this any mat file. So I have to do it, this one. This you have to write data dot atom dot and so this is the n-type doping. So you can see the concentration is here. So if you have to calculation, this is the doping concentration. This value is 3.996 percentage value. Doping concentration of 1000. Okay. Now this way you can create their virtual approximation value. Okay. If you have to do with this p-type doping, you have to simply yeah. If you write data, that data value also you can see here, and you can see if you write data dot this is a description for this VCA of silicon atom. So you can see that this is the concentration for the end. It was a N type doping. Okay. So this way you can create the VCA input file. So by using this VCA input file, we will try to doping of the any devices. Okay. So first we have to make the device. I will try to make a device with silicon and try to dope with the silicon concentration doping. Okay. So I'll have to take it the some specific. I have a uh, CIF file. I will open it. So import local, and I will take from the here, and I will take this. This is a silicon 100 atom molecule in which different their coordinates point. If you wanted to see the coordinate point, if someone wanted to make this structure, I will show you. This is you have to change their atom position, atom coordinates with this coordinate. You can see here, this all coordinates are given. Now we have to make the structure. So I'll take the redefined crystal. So you can simply, and I will be expand it into the in the Z direction. So I'll let it be seen. Yeah, right. Okay. Now you can see here. This is the your. Now I have to build. Now I wanted to create some. Now I wanted to make this molecule crystal into the device form. You know, as you all know, there is a build. This is a convert to device option. We have to select the left and right electrode. You can see automatically some default value of thickness is selected. Should I preview? Yes. When I click preview, the structure is ready. Now this is the left electrode, this is the right electrode, and this is the middle one. Now I have to add some buffer. If you wanted to add buffer into the any center region of the device, you have to simply go on simulator. Then NanoDcal, there is an add buffer option. I will take it and I will be add some buffer. So let it be see. You can simply do it. It will take about you can see this increasing and so I will take it. Go to the so this way you can increase the buffer between the any central region of. Okay, now click build. Now this is your buffer structure. Buffer is ready. Now your device is by using this method, you can also create any device of nano level. So now we have to add some doping between this structure. So when you click, yeah, before the creating, before doing any type of doping, if you wanted to dope with gallium arsenide, you have to first take the VCA, that is virtual crystal approximation input file for N type or P type as well. Okay, from here. Now then after you can choose like this structure is ready. Now I have to dope it. So I have to do the doping. So you have to simply go on. You first have to select this means file will be selected for this device, in which device you have to dope. So simply you have to go on simulator option and then NanoDcal. There is a SCF calculation. When you go into the SCF calculation, their pop-up window is pop-up tab is open, in which you define all the SCF parameter, like their electron temperature, energy cutoff, exchange correlation value. If you choose the PB, GGA type, that is a generalized approximation, this is a local density approximation. This way you can select it. And if you wanted to give some standard key point sampling value, I have some standard I have value some for this device. So, so I'll select it. And, so I'll take this value. This value will be default. And for case point sampling, I have value. This value 10, and this value will be also 10, and this value will be 1 also. So now the next part is, if you wanted to change their integral lower bound, and if you want to give some value to the electrode, and someone wanted to give some energy, like and someone wanted to set the basic set, and this is the spin type in which you are set the collinear or general type of spin you can perform. So here the doping option, you can see here in the basic set there is a doping option you have selected, and you can see as already default is selected. Now you have to do, first you have to go see you not necessary you have to select this, but you have to go on user define. When you go to the user define and select that file directory where you perform the VCA calculation for the specific material, like gallium. So that project gallium arsenide, and you can see later what name was the silicon. Yeah, this. See, this is your crystal matte file generated for your silicon VCA input. Okay, this value you have to select it. Like I have to do, you all know this is the p-type doping, this is the n-type doping parameter matte value. So I will select when it. So I'll select it, open. So after the selecting this, you have to click search. See, your device is shown here. Now you have to define how where you have in which region you have to do the doping. When I have to select this this like this. When I select, you have to simply double click and slide. When I go here, then see this region is selected. Now when this region is selected, you have to simply click on select. See the select region, this region is select. Now you have to click on OK. So that means that region you are selected, that means it is doping with p-type doping is completed here. Now we have to do an n-type doping. So simply click on plus icon. If there is another type of element, if there is another type of molecules or atoms are given, you have to select, you can select from here. Okay. So this is all depending upon you, what type of structure you are making. So see here, this is the default value I selected. You don't have to select this. You go to the user define and go where the VCA calculation, which is you doing earlier. So in webinar, I'll do it for here, NanoDcal, and this was the n-type doping. So I'll select it and see. And after the selecting this, you have to select the region where you wanted to do n-type doping. So see, this region was already p-type doping, and I'll do it from here. Okay, let it do again. Okay, maybe it is like I have to select this region. Okay, now this region is selected. You have simply click select. When you click select, this region is selected and click OK. When you click OK, that means the N type doping and this is the P type doping are selected. You have simply click on generate file. When you click the generate file, that means this region is P type dope and this region is N type doped completed. Now you have to now you next you know all the things about what next things you have to do. You have to simply calculate the parameter. This is the if you wanted to see the things like if you wanted to open with, then you click open with C. Here, when if you wanted to see our doping is uh, perfectly selected or not. So simply when you since you I'll open it the left electrode, you can see here in silicon in atomite. This is the left electrode. In electrode, this four atom, which is since you can all see in this is the left electrode there is a four atoms of carbon or silicon. You can see this is associated with VCA slash silicon or silicon zero means 0.0999 value. So this value is P type value is selected. Now, if you wanted to see in right electrode, you have to simply go on open with. You can see this is the right electrode. There is a atom system dot atom log. How many atoms are there in left electrode? This is the four atom, and this is doped with PCA dash silicon one. That one stand for 1.0001 value. Okay. This is the default value are selected. If you have some another type of concentration, you can calculate them according to your projects. Now, if you wanted to see the what regions are, if the regions of centers are perfectly doped or not, so you have to simply go on open with and some expand the things, and you can see as half of the values are doped with silicon. One value, one stand for the one shows the concentration, and after this zero started, that means 0.99. This way you can do the doping in the calculation. So if you wanted to see the another parameters, you can see their temperature, energy cutoff, and you can see here description of electrode. If someone wanted to give some voltage, so you can like I have to give the voltage. I selected -1 voltage to 5 voltage. Okay, this way, or you can save it. This when you save it, this device is having with some voltage. So currently we don't need to voltage. So this is the description for where the left electrode is saved. This is all automatic take the central region when you perform the calculation. So you have to first calculate the left electrode and then right electrode. Then after central region. You all know one is completed, then another one is will be started. So it is in cube form. You can see here all three calculations are there. Now next, if you wanted to calculate their band structure, like another type of structure like band structure, things. No, sorry, this is the device. In device, there is no band structure. In material, the band structure are. Someone asked me question. Okay. Lot of math. Okay, if someone wanted to calculate the any type of parameters, they can calculate them like total energy, density of state, their effective potential, scattering state, transmission, photocurrent, IV curve, charge, electron density, for potential conductance, thermoelectric current, Seebeck coefficient. All the things you can calculate. If someone wanted to make this structure, this transistor for this, you can calculate them. And this way you can perform the any diode, and if for the specific, for the different type of material according to your project. Since I have already calculate some values, I can show the for this software for this device. So I'll show you. You can see here. This device was same, which I explained you, in which I tried to calculate the things, like I calculated the effective potential, and you can all see this is the effective potential of this silicon doped with doping type structure, in which you can see the effect of effective potential. If someone wanted to see this data into 2D1, you can see here, and in stereoscope you can see the data, and along the Y, along the Z. Okay, you can also see in plane display. You can see the plane display along the Y, along the X. And if someone wanted to see this data into 1D graph, you can see this is the 1D graph value of the effective potential of this device which we are creating now. You can calculate their values. If someone wanted to see the data into some specific thing, they can select from here, and they can adjust their size as well using this tool. Okay, now I'll also calculated their total density of state. So I'll show you. This is the total density of state value. Uh, if someone wanted to zoom it, you can simply go to this. There's a tool named. You can see this is the total density of total electron density. Someone wanted to see in 2D. You can see this is the stereoscope data. This is 1D. This see the effective value are here, and this is the total electron density value. And if you want to see the density of state, you can select here. This is the density of state of this this device. You can zoom it. Or someone wanted to see this data in some specific range, they can select them. This is the origin, and this value you can see the all data are shown here. This way you can calculate the many of things, all which you can see here. And transmission output, you see this is the transmission output of this device. So this I think this calculation was take some 4 to 5 hours something. So if someone wanted to calculate it, they can calculate it easily. So not these calculations time are depending on their as I earlier say many times, their devices which are used like desktop or server. These things are all depending on them. Okay, but our software can calculate the more efficient way to the any parameters. That is the main things our agenda to show you. So by that method, you can see the you can create any type of diode with different type of material. You have a license and try to practice and try to make the different type of diode with different material and calculate their parameters. I hope I assure that you will get the exact values and perfect value, not the perfect one, but you can the perfect values. So now we should go to the next part, which I have to calculated that photo current, etc. Uh, so I'll cut it. So if someone wanted to calculate the photo current value, as you can see here, this is a nanodecal and SCF calculation. When you go to the analysis part, there is a photo current. Photo current is also a very effective parameter that help to the into the some specific researches. So I have a device. I'll try to make a device, and I'll show you how can you uh, get the photo current value and how can you simulate them. So I have a value. I can show you. Uh, I'm going to make that structure. This is a very easy structure in which I work with WT2 device. I show you. This is a research paper of that was a non-equilibrium spin injection in mono layer black phosphorus type device. No, this is not. I think I forgot that. So give me 1 minute. I'll show you. Okay. So I have a device. I wanted to show you to all of you. I think I was seeing in the research paper was there enhanced photogalvanic effect in the two-dimensional WT2 device monolayer vacancy and substituting doping. In this device, there is also a doping type structure, where we doped a single atom of gallium into the WT2 device. So I wanted to show you to all of you and try to calculate photocurrent. And I will show the result with similar project. So first I have to make the let me to make this structure. I'll show you. So you have to first I have to go on. I will take the material from online directory. So import online and WT. Simply click enter and see this is a different WTD device different with different space groups are coming. So here I'll have to choose this one. So I simply click on add. When I click add, this is the molecule I will take it. So I'll have to, if someone wanted to change their orientation, they can choose here. So first I have to delete some atom from this. So I'll have to take this one. So I have to delete this. So simply there is an option and delete atom. So now this I have to perform the make the structure via this molecule WSO2 molecule. Where let them make the center. Now, so I'll have to change their orientation. So to change the orientation, you have to do with this. You can choose here. You can see, and I'll have to also do this. Let me select correct parameters, correct values. So okay, now we will doing this structure with this type of orientation. So now I have to go on build option and redefine and see click preview. When I click preview, I think this is not selected perfectly. This value will be one. Okay. So if someone wanted to perform this uh, device, they can also do. Let me start it with a scratch. I think I'm doing some mistake in since space their coordinates are also matter. So mm, that should do work. Bioelectric. Let me do it here. I have already a project. After this, I will be demonstrate. If someone wanted to work completely with MATLAB, I will be show you all the things how to use in MATLAB. So in MATLAB, there is also a good things. If anyone more familiar with MATLAB, they can calculate all the things into this MATLAB. So I will take the orientation which I need for this calculation directly. If someone someone wanted to know how I change their space group, they can ask me directly. So after the session, let me copy this. Let it be. I have to already show here. So I will copy it and I copy. I have to with this orientation. So you can see I have to expand it into the some standard direction. So redefine crystal and with 3 and 8 and click preview. Now this is the WSC WT2 molecule, and you can click build. You can see here, and if someone wanted to see in their different orientation, they can select them by that way, and you can see now this is the orientation. Now, if someone wanted to do replace some atom, like I will be replaced, like I have to replace some W atom. So I'll have to delete this. So you can simply select it, and this is the delete atom. See, this atom is deleted. Now I have to dope a gallium into this WTET device. So here I will be deleted, and I wanted to make this or atom into the gallium. So you can select it, and there is a replace atom. When you click replace atom, there is a periodic table is open. Now you have to select the atom you wanted to dope. Since I have to dope gallium, so I click OK. Now you can see here. Now in this device, in this crystal, there is a molecule called gallium is added. Now we have to perform calculation with it. Okay. Now we have to make this crystal into the device. So you all know there is a build, convert to device option, and give the thickness of give the electrodes. I will be take the top and bottom electrode. Since the thickness is sorry, default thickness is shown here. In, yeah. This is the default thickness. As if someone wanted to change the thickness, they can change according to their convenience. So click preview. When you click preview, now this crystal makes made a device form. So you can click build, and when you click build, now this is your device of WTT device with gallium doped. So if you wanted to see in different orientation, you can see here. Now this is the armchair direction, and So now I will tell you the how you can get the data, how can you calculate the photo current for this via this project, okay, for this device. So you can do with some if you're making some another type of device, so you can create it before the calculation, before the doing the any analysis. You must have to calculate there as safe into input. So you have to go on simulator NanoDcal and click SCF calculation. When you click SCF calculation, there is a, you all know, their key point sampling, their different type of parameters is shown here. I can show this value will be one, and this all value will be default one. And in electrode or a control integral, if someone wanted to change the value, they can change. Uh, and this way, you can do the values, give the values, and all things will be same. And I will click generate file. See, the generate files is clicked. Then run it. You know, first you have to run the electrodes and run it, and after device. Now this is the main thing we have, which is we have to calculate the photo current. You have to simply go on simulator and then NanoDcal, and there is an analysis part. See, this is a photo current. Photo current. Okay. In photo currents, you can see the parameters are shown here. What type of polarization basis you wanted to give. So you can give their values, and if someone wanted to see the polarization vector, there is a basically a linear polarization, left circulatory polarization, right circulatory polarization, elliptical polarization, oblique elliptical polarizations are given. And you can change anyone according to your changing the polarization. Their parameters, well, parameters calculations topic will be also changed, like what type of things they needed, they will be confined here. And like I will choose the linear polarization, and you have to put the theta value, minimum, maximum, and how many interval you want it to give between the minimum to maximum. Okay, so I'll be choose here. I have to choose 180-degree. Minimum is 0, 1, and this will interval will be 115. And this is the photo energy range in which you define how energy will be fall into that device, and that will be calculated for different state 2.80. And this is the some values are I have. This is the A minimum, and this maximum B will be same, means that value will be constant. This minimum and maximum energy will be same. That means energy is constant, and their delta value will be 0.10. And from here, you can change you can get their key point sampling values. And now the next part is, this is the edit the irradiated atom, in which atom you wanted to perform the photocurrent. You have to all select one. You can simply double click and slide down and select all and select. When you select it, the atom indices are ready. Now you have to click OK. Now the next part is click generate files. After the clicking generate files, the photo, that is phc dot input file is in. You do not have to calculate immediately. No, you must have to put the photo current dot partition scheme. This value is defined the electrode of this device. So first you can see here, this is not default things. You have to do with yourself. So simply first you have to uncomment. You know all this percentage means comment value. And before the doing this, you have to go your device like I'll go into the Y, and you have to see the electrode, what electrodes are there. So simply select our left electrodes are this. If you wanted to see the information about this molecule or structure, simply click on here is a label. When you click label, if you wanted to give the label, I will take the yellow color and apply. When you click apply and see, so see, this is the number of atom. This is the define the atoms number with okay. So in this in that PSC dot input, you must have to define this number. We are defining this number. The input file is understand which is your electrodes are there. Okay. So like this is the first way, or second way is you have to simply select this left electrode and right click and display atom. Okay, when you click display atom, you can see here there is a lot of files. There all the atoms numbers are shown here. You must have to see like 108, 109, 108 to 125. That means 108 to 125 atoms are electrode, left electrode. Same as at the right one, you have to simply select the left atom. Yeah. You can count, you can do it with your count at your own, and display atom. You can see uh, from 126 to 143. These all are the our electrode. So this value you must have to put here. So open with, and here in which you must have to the value for the 108 is 2. You add this 108 to 125. Now next 125 to what was the, I think, select here and display atom 143. Then select 143. Now click save. Then after performing this thing, then you must have to run this photo input as well. Okay. Now see, this is in running condition. I already calculated. This will take the time according to, since the DFT calculation takes the time. So I already calculated. So I'll show here. I here this device is same. I made it. You can all see this is the same device. Now here I calculated the different parameters. Like this is the transmission input, transmission coefficient with energy graph, and I also calculated the conductance, effective potential, total energy, scattering state, charge, electron density, potential dot input, conducting. These all things are calculated here. You can see if you wanted to see the show view, I'll show you. This is the total electron density are shown here. You can see in the 2D model, you can see here. And if you wanted to see in, with different uh, along the X, Y, Z axis, you can see from here. And in 1D graph, you can see this is the total electron density graph. And after this is the effective potential. So this you can see here, this is the effective potential graph. You can see I calculated. Now 2D graph, this is the 2D potential when effective potential and stereoscope. If you wanted to see in along Y, Z axis, you can see here their effective potential. And in 1D graph, You can see this is the effective potential graph along the YZ plane, along the XZ plane. This graph will be shown. Okay, now I calculated. So I did not show you the Seebeck coefficient. So I calculated the Seebeck coefficient of this device. This is the Seebeck coefficient I calculated, and in which you can see here, if you wanted to see in temperature value, so you can see the temperature. If you wanted to see in chemical potential energy, you can see here. Uh, uh, you can see here. This blue line is shown for spin up, and this is red line shown the spin down uh, graph. And if you wanted to control it, you can control from here. If you wanted to see the specific data into some ranges, you can select from here. And you can also give the color according to your convenience. Like I'll choose this. So, okay, you can see here the line color is changed like this. And you can also do this. You can see if you want to change, take the another color, like I take the blue one. You can see this way you can change the color also according to your convenience. You can change the name also. And there are many things of this software out here, but the main thing you have to perform it, and when you explore it, when you having the more familiar with it, you can able to see the many things and many know the many things about the nanomaterials and nano devices, and going to be more familiar with them. So this way, density of state are already there, also there. So you can see the density of state for this device. This is the for all the atom. How many atoms are there? All the atoms are there. If you wanted to see for a specific atom, you can see here, and you can change also them. So this way you can see the data, all the data. Okay. Now, still is running. Now, since the photo current of this structure is not completed, but I have calculated the some another type of photo current. My main agenda was to show the things what you can do in this software. So, okay, I have calculated photo current. Since this photo in this device, I did not calculate it photo current. The calculation was not perfectly happening. So I have a second project which is same like this WSE2 device. I'll open it, and I have to open this when that project, which is this WSE2 device. This is the same type of structure in which I calculated the photo current. I wanted to show you. In this, see, you can see the photo dot input are shown. Now for photo input, for photo energy, photo current, you must have to go on MATLAB and see the parameters there. So you have to go on MATLAB and get the directory, file directory. I do it directly. Okay, now this is the file directory in which I calculated the photo current. So I wanted to show you. I do this project with different doping, concentration, and a lot of things. I do it. I done it. So you can see here photo current is calculated. You can simply load this photo current data and type data. You can see the data are given. This is the photo energies. If you wanted to see the photo energy, you have to simply type data dot photo energies and some description you wanted to see. And the main thing, the photo current graph. So you have to simply, this the photo current dot figures are generated, and this is the graph. Okay, this is the graphs are generated for this device in which for lead 1 and lead 2, two type of graphs are generated. You can see here. Uh, this way you can get your photo current data into the structure. Okay. When you perform this photo dot input file, these figures are we get it. So I think I demonstrated the I was trying to all to show the all the of the things from this structure and calculation. So here I will completing the I will closing the device studio, and I think I saw the all of the things in the this device studio and calculate all the parameters. And please, I have to request to all of you perform the calculations with the materials and devices, and as well as you will be familiar with all many things with this device studio and NanoDcal software and rescue software as well. So the next part is the main thing. Some peoples are familiar with more familiar with the MATLAB and does not wanted to. They have a lot of information about the CIFR. That is a crystal information file. Uh, in that file, like whenever we since I'll have to show the things what I have to I wanted to show you. Like whenever we are creating a project, like I doing from the scratch. So close it. I wanted to show the some specific things in like close. I close it the all window, and since create when we are creating a new project, like creating a new project, okay, and what is the exactly things are happening in this software. So I wanted to show you, like I click, name with MATLAB, uh, a file with MATLAB. So this webinar I'll name with MATLAB. Okay. So I'll save the MATLAB name. So what exactly things are happening? Like uh, when we are since in starting of the webinar, I was telling you that our software, which is a NanoDcal DFT calculation software, and rescue also, it all is written in MATLAB. Since you know the MATLAB is a syntax code, having a syntax code as C also have. So this all calculation are running in background in MATLAB code. So whenever we start the calculation, when we are doing a calculation or when we are making the crystal information, whatever we think, this their script are generated in the MATLAB file, MATLAB script. So when we are like taking, I will go into the file and open project, no, creating a new one. So import online. So I'll take like local that I so 3D materials and semiconductor, and I'll take the silicon. See, when I take the silicon, but here you can see in the user interface you can see the silicon, but what the exactly are happen in the that file directory. So I will close it, minimize it, and go. I will go to the that file directory where I created this project file, the webinar. See here. Just MATLAB. Okay. When I click, when I create this, let it be deleted. This one. We did not need this one, and this one we did not need. I'll paste it here. Uh, Let it be deleted. No problem. I pasted it. So see, when you create a MATLAB file, so whenever you generate a MATLAB from the device studio, there the two things are generated. The first is that HCF SPF file. This SPF file is help you to open the existing project. And when you go to the MATLAB directory, there is a two things are generated. First is work.xml file. A second is silicon.hzw file. Since you take the silicon atom from local directory. When you take the silicon atom from local directory, there is a HZW file. You can also say this file name CIF file. That is the crystal information. Okay. When you click open, see when I open it in Notepad, you can see here. This is nothing but this is a simple coordinates of the data. Okay, where this atom will be seen in space, how what their vectors are there in x y z. Okay, only the things is their coordinates are given. So by using, if someone has the good knowledge about the how to write the script of the crystal, so they can do the very they do not have need to use the device studio. They have only sufficient the MATLAB and our software. And if someone have the good knowledge about the device studio or things, okay. So this way you can do this, and this is the silicon. Now I will try to do the calculation this silicon via this MATLAB. Okay. So when I click MATLAB, you can see here when I have to go there MATLAB. See here I have saved this file. I think that's it. The directory was there. See in MATLAB. Okay. I simply browse this. I'll let it be clear windows. Okay. So you can see here. Then there is no input file. There is nothing. Things are given. Okay. The thing is you must have to first you have to generate the SCF input file like simulator.nanodecal, and this is the analysis, and I analysis, and like I have to calculate the SCF file. You all know when I click SCF file, you can see here when I go here, see there is also a file that is available called SCF file. Okay, see the nanodecal slash crystal. When I click the SCF file, I generated the SCF file. There is a silicon LDA-DZP double zeta polarization. That means local density approximation. This is the method of solving the calculation. This is a exchange collection function. You must have this file and .NET. That not matlab nano means I think mat files something name or and when did you not have this file, this calculation will be not happen. Like I will be remove it, like I'll cut it, and I can will copy it. I can copy it, then I delete it. Okay, see I delete it. So see there is a scf dot input file. I have scf dot input file. I have to simply do nanodecal, right? Nanodecal dot scf dot input. When I click it and that, click enter, see let it now You can see warning escape. There is not, I can see here, the calculation is not running. So because I don't have the NAD file. So okay, I have to paste it here. This thing, huh? I think there is some problem. I'll do it again. Let the thing. Delete this. Do it again. And so okay. Cancel. So the silicon LDA DCP.NET files are there. Now I will be try to uh, run this input file. So I have nanodecal dot scf nanodecal scf dot input file into this one, this thing. Okay, I'll click enter. When I click enter, you can see here the calculation will be running. Okay, now you can see, now you can see the calculation is running into the MATLAB file. Okay, and there are different type of mat files are shown here, and all the calculation now is running into the MATLAB. Okay, by that way you can calculate the. You can also use the MATLAB to run your calculations. So since I already since you can if you wanted to do this calculation, you cannot do this because you don't have the environment setup. So to see the environment setup, how you calculate the things into the MATLAB, we have a video on YouTube. That is, I'll go here and I show you MATLAB integration name. I'll go there and type impulse. You can see here we have a video how to set up the environment of MATLAB into the for the NanoDcal. So uh, after the performing, if someone not able to do this, they can also ask us how you will get things like in MATLAB. See here this video, MATLAB integration, in which we are defined how you do this calculation on the MATLAB. Also, on the see, we are complete doing this integration onto MATLAB, and okay, by that method you can all do these things on MATLAB. And if someone want to have to more interested to do this calculation on MATLAB, I have many things and many more information about this MATLAB. They can directly ask me, since I don't know how many persons are working on MATLAB, and maybe there is not no one will be also there who does not wanted to do this calculation on MATLAB. They most of them the preferably because our user interface is very easy, and you don't have to, if then someone not wanted to do this calculation on MATLAB, they have a user interface. They can simply run it from here and they can perform the calculation. So like I have to calculate the band structure. I'll show you here. First, I have to create the band structure input file. So I will go on simulator NanoDcal analysis and band structure. I will click generate file. Okay, for MATLAB, no worry. If you have to any question, you can ask me. We are there and perform. Try to do these things on MATLAB. If you did not get any information, you can ask us. So this is the band structure dot input file is generated. Now go to the here. This there is also a band dot structure dot input file as shown, and you can type NanoDcal band type as it is shown here dot input. Before the calculation, I wanted to show the things what the script has there. So when you click it, you can see the band structure dot input file is shown here. Since this is the since we did not need, uh, uh, I will tell you earlier that a calculation dot control dot xml equal to true is visual in, realization for the device to give. But if you wanted to see the data, see the graph into the MATLAB, you must have to uh, uncomment this calculation dot band structure dot plot section. So like I will be do it comment it. So I do not need this here. So I then click and uh, type type this and control plus S, that is save. You can also save from here and save. Now I have to run it. So I'll run it. See, running is started and all the things are doing. The person who are working, see, the band structure is showing me here, and your calculation is all calculation are completed. They are village union path, and there are different type of parameters you can see here. And the visual, the band graph structure figure is shown here. Okay, so this way you can also perform the calculation on MATLAB. If someone having work with the Raman property, optical property on rescue, there is also things is for calculation on MATLAB. I'll have to show it. So for MATLAB, I already have a setup. So I'll first have to make the structure, make the input file. So simulator, I'll go to the rescue and like I have to calculate SCF calculation and I'll click generate file. See, this is the rescue file. Then I will be go on there and MATLAB and I'll have to go into the that rescue file. So in this file we are coming. So for this, I'll have to type this some description, some syntax. So let me do it. Like I'll typing rescue. Mm, like it completed now. Uh, like type here you have to type for rescue calculation on MATLAB. I'll type rescue. slash I, and we have to calculate for silicon. So for silicon and SCF dot input, I think. Click enter. I think there is something missing. Rescue and I SCF dot input. See, the calculation is running into the MATLAB file and their output are also generated. Now that method, you can calculate all the things into the MATLAB as well, into the rescue also. So now the next part is, I think we don't have things is currently remaining. So if someone wanted to ask some question, they can ask me also. Then I will be off this meeting. Diodes. See that. Diode, I made it the PN junction. Anyone, any question regarding the tools? Quantum for quantum capacitance, we have a paper. So you can read it and try to perform them. Like I have to go. You must have to, if you wanted to see, you can I copy it. Click enter. You can see there is a quantum transport study with NanoDcal software there. Yes, you can perform it. You must have to try to explore the software, and I hope you will be able to do this quantum capacitor also, because yes, you can do it. The process of analyzing the graph results and things are all the same. We have a lot of videos on YouTube, so you must have to go there. There is a number of videos. You try to we give electrodes to we give a license to you, so you can go here and there are a lot of videos. And I have also performed a lot of things in which I showed you to how to analyze them. And you can see there are a lot of videos. And for diode results analysis, I mean, Another question. So if someone, I'll be closing this session. If someone not have a question, if someone have a proper some specific question, they can directly ask us. And we are here to help you. And as- like the let me in MATLAB, the things two four things are I have to also show you for NanoDcal. It's like NanoDcal dot basis. When you click, you can see the basis of the file. It's- yeah, tell me. Okay. So I will. If someone have the any question, so they can also ask me, and we are here. Any type of support you need it, they can also ask us. And we have a lot of things also on YouTube. And try to familiar with the software, and they can. I hope if they can explore here, they can give the best information. So thank you to all of you to joining us and give your precious time to be us. Thank you, everyone. You can leave all. Can all leave.